in the classroom to be very interested in science about energy because energy is everywhere. And I'm going to show you a little bit of energy right now.
Whether it may be to cool or heat your home, drive a car, lift some weights, or even cook your favorite meal, energy serves a very important role in our everyday lives. It's everywhere and present in all different kinds of forms, whether it be mechanical, elastic, gravitational, or even kinetic. But those are just examples. What does all of that really mean?
Well, first, it would be beneficial to give you, our viewers, a general explanation of what we will be covering in this unit. Energy is the ability for any object to do work. It is the basic influence required for any action. As for our examples mentioned prior, there are various types of energy, all of which fall under one of these two categories, either kinetic energy or potential energy.
Potential energy is the stored energy held by an object because of its position relative to other objects or positions. For example, chemical energy is stored in food. As we feed, our bodies transform that energy into moving energy like heat or mechanical energy. But there's also a possibility for potential energy to be due to an object's location. This type of energy is typically a general term, as there are many underlying types of potential energies. One of which is elastic energy, and that occurs when an applied force causes a deformity on an elastic object, like a bow and arrow. And there's also general gravitational energy, which is energy due to its location. Example, somebody holding something at a specific height.
All in all, an object that possesses potential energy, due to its location, has the ability or potential to move. Now, another type of energy that we'd like to speak about today is kinetic energy. Kinetic energy is defined as the energy that an object possesses due to its motion. Now, all moving objects possess kinetic energy. For example, a car driving down the street or an object rolling off a cliff. Now, how do these two types of energy correlate, you might ask? Well, there's a concept in physics that we like to call the law of conservation of energy. Now, the law of conservation of energy states that energy cannot be created nor destroyed. It can only be converted or transformed from one form to another.
Is there any way for this to be calculated?
Glad you asked, my fellow scientists. So, since our focus today is on kinetic and gravitational potential energy, we have two different formulas that we use to calculate these two forms of energy. To calculate gravitational potential energy, also known as EG, we use the formula EG equals mgh, m being the mass of the object, g being the acceleration due to gravity on Earth, and h being the height of the object above a specific reference point. Now here we have our equation for gravitational potential energy. Eg equals mgh, m being the mass of the object, g being the acceleration due to gravity on Earth, and h being the height of the object above a specific reference point. Now, I'd like to start by defining the term energy. The definition of energy is the capacity to do work. Therefore, the definition of gravitational potential energy is the capacity of gravity to do work. Now, let's say I'm holding a ball a certain height above the ground, right? Now, the forces working on the ball would be Fg and Fn. Now, let's say I let go of that ball. Fg would do a specific amount of work to bring the ball to the ground. So let's say the force of gravity does 100 joules of work. Well, we know that because of the definition of gravitational potential energy, the work that the force of gravity needs to do to bring the ball to the ground is the gravitational potential energy of the ball. So if gravity needs to do 100 joules of work to bring the ball to the ground, we know that the gravitational potential energy of the ball at this height would be 100 joules. If it was 2 joules, we know that the gravitational potential energy of the ball above this height would be 2 joules. Now, let's prove this. Gravitational potential energy is equal to the work done on the ball, right? Now we know the work formula is work is equal to FA d cos theta, right? Now FA being the force that's going to be doing the work on the ball, which is Fg, d being the displacement, so the height that the ball will fall through, height, and cos theta, theta being the angle between your force that's doing the work, which is the force of gravity, and your displacement, which is your height, or the direction of your displacement. So we can now say that work done on the ball is equal to Fg h cos, and then the angle between Fg and h would be 0, because they are both going in the same direction. Cos 0, which we know is 1. So now we have work is equal to Fgh, and we know that Fg is also equal to mg. So if we know the mass of the ball, and we know that the acceleration due to gravity on Earth is 9.81, we can say that work is equal to mgh, or e.g. gravitational potential energy, which is equal to work on the ball, is equal to mgh. E.g., that is how we derive our formula. E.g. is equal to mgh.
Our second main focus for today is kinetic energy, also known as EK. The formula we use to calculate kinetic energy is EK equals 1/2 mv squared.
But how do you derive it?
Okay, so now we're going to be focusing on kinetic energy, and the formula for that we know is EK equals 1/2 mv squared. But where exactly does that come from? So we know that work equals change in EK, and we want to focus on that and remember that throughout when looking at how this formula comes to be. We also know the formulas F equals ma, and the kinematics equation v2 squared equals v1 squared plus 2ad. And when we look at these two equations, we notice that they have a similar variable. So what we want to do is we want to isolate for acceleration and then create these two equations to equal one another. So A equals force over mass, and acceleration equals v2 squared minus v1 squared over 2d. Now we're going to make them equal to each other. Force over mass equals v2 squared minus v1 squared over 2d. So what we're gonna do now is we're gonna multiply the numerators and this numerator with this denominator, this numerator with this denominator. So this one would equal force equals 2 times d. Force times 2d equals mass times v2 squared minus v1 squared. So now we're gonna isolate for fd. And we'll see later on why that's important. So we just divide that by 2, and then whatever we do to this side, we have to do whatever we do to this side, we have to do to this side. So we're going to divide this side by 2 as well. That cancels out. FD equals, now we're going to distribute mass to both sides. Mass over v2 squared over 2 minus mass v1 squared over 2. And we always want to assume the initial is equal to 0. So this side cancels out, and then all we have left is FD equals mv2 squared over 2, which is nothing but this is work, which is also FD cos theta. And then this side of the equation is nothing but 1/2, when the 2 makes a 1/2 mv squared. So what we did here is nothing but work equals change in EK. Our kinetic energy formula is 1/2 equals mv squared.
Now, right now, I'm going to prove using unit analysis that energy is in fact measured in joules. Now, we previously defined energy as the capacity of an object to do work. Now, we know that work, which is also measured in joules, is equal to FA D cos theta. Okay? We know that FA is measured in newtons and D is measured in meters. So we can confirm that 1 joule is equal to 1 Newton meter. Now, if we look at the formula for gravitational potential energy, we know that Eg is equal to mgh. M is the mass, which is measured in kilograms. G, acceleration due to gravity, meters per second squared. And then the height is measured in meters. Now here we have kilogram meters squared per second squared, and we know that 1 Newton is equal to 1 kilogram meter per second squared. So here we have 1 Newton meter. Therefore, gravitational potential energy is in fact measured in joules. Now the same is true with kinetic energy. If we use the formula for kinetic energy, we know that Ek is equal to half mv squared. Now, you have mass, which is measured in kilograms, and you have your velocity squared, which would make that meter squared per second squared, which again is 1 Newton meter, because 1 Newton is 1 kilogram meter per second squared. Therefore, we have just proved that kinetic energy and gravitational potential energy are both measured in joules.
These two formulas can correlate to one another depending on certain exceptions in the question. So as a quick demonstration to show you guys how the idea of conservation of energy, we're going to drop this ball. So the first thing that we have to ask at 3 different locations, we're going to look at the top, the middle, and the bottom. So we're going to ask ourselves, 1, does it have a height? And 2, does it have a speed? So at the top, when I'm holding the ball just like this, it does have a height, but it doesn't have a speed. So the only present energy we have is Eg. When I drop the ball and it reaches the middle, it both has a height and it has a speed. So the total energy would be Ek plus Eg, which is Ek is when there's motion, and there is motion when it's dropping, like it's in midair, and there's a height above the ground. But once I drop the ball all the way and it reaches the floor, it doesn't have a height because it's like at our relative position, but it does have a speed. It has our impact velocity. So the only present energy there is Ek. Okay, so what do we know? We know that we know the mass, which is 5,000 kilograms. We know our relative position is ground, which is, we can assume that that's 0. And we also know that it starts at rest, so A does not have kinetic energy. So what energy is present at each point? So that's what we're going to look at now. So at A, since we know it starts at rest, it doesn't have Ek, but it does have Eg because of the height of 73 meters. Next, we look at point B. Point B is going to have a speed because the roller coaster is going to continue on, and it's not going to stop and then continue going. So it has Ek, and it also has Eg because of the height of 20 meters. Then we look at here, same to point B, this one has both Ek and Eg. So, okay. So now we're going to look at A. So since we know it's only Eg, we have the formula Eg equals mgh. So we have mass, the gravity, which is always 9.81. That's like the universal gravity of like the Earth. and then we have a height of 73. So we sub everything in, and we find that the gravitational energy at A is that number. Now we're going to look at B. So when we look at B, we know that there's kinetic energy and there's gravitational energy. But we can't just make E total equals those two, because that's not going to give us relative to the ground. So we're going to look, and we're going to use EGA equals EKB plus EGB. We're making them relative to each other. So we know the answer to EGA, which we calculated beforehand, is that, and then EK is 1/2 mv squared, and then that is mgh. We sub in what we have. We don't have the velocity, so we do everything, and then we substitute, we find velocity that way. Sorry, it leaked through, whatever. So we find out, we sub everything in, and we isolate for v2 squared. We square root that, and then we come to the conclusion that the velocity at this point is 32.25. Since it's 2 sig days in the question, we round that up to 32 meters per second. So going back to the question, it's asking us for to kinetic energy and the speed. So EK, we sub in what we got. Now we have no unknown variables because we found velocity. So we sub all of those in, and then we find that our answer for kinetic energy at point B is 2.6 times 10 to the 6 joules. Then we sub in for EG, which is mgh, and then we find that it's 981,000 joules at point B. Now we're going to do the same process for point C. So at point C, we concluded that there's EK and EG, and we made that relative to EGA, which is what we did for the previous part. So we make them all, we make EGA equal to those, we substitute everything, we isolate for V2, velocity, because we don't know what that is. So we do all this math, we find the answer, subtract it from both sides, and then we divide, that's 250, divide that from both sides, and then square root it, we get 9.9 meters per second. So that's our velocity at point C. So now since the question is asking its total kinetic energy, we sub that back into our equation and find that our total kinetic energy at point C is 2.5 times 10 to the 5 joules, and then our EGC, which is our gravitational energy, is 3.3 times 10 to the 6.
Alrighty, so after doing some research about the law of conservation of energy, we were able to come up with a household demonstration, or with a demonstration using household items that is quite simple. So all you need is some string, some scissors, 2 chairs, and 2 masses. I used water bottles. So you're going to start by placing the chairs a certain distance apart. Then you're going to tie a string between the 2 chairs, and you want to tie 2 strings to the string that you tied between the 2 chairs. You want to make sure that these strings are of equal length, and then you want to attach the masses to the bottom of each string. Now that you have your system set up, you're going to swing one of the water bottles or masses, and you're going to watch as this one stops, that one continues, and again, that one stops, this one continues. You can see that the water bottles are switching behavior. Now this demonstrates the law of conservation of energy, because the law of conservation of energy states that the total energy within a system remains constant, irrespective of the internal changes within the system. And so you can see that when I swing this water bottle, the energy is not lost, but it is only transferred from one form to another within the system. So the law of conservation of energy actually states that energy cannot be created nor destroyed, it can only be transferred from one form to another. And as you can see, as they swing, the energy is being transformed from gravitational energy to kinetic energy, back and forth. And so the total energy within the system remains constant.
What would happen if suddenly there were no energy in the world? Well, first of all, there would be no electricity, so the wouldn't they? And then the wind wouldn't blow anymore, so the clouds would stop moving and the flag would stop blowing. There would be no more movement. The cars wouldn't move. As a matter of fact, all the lights would go out. Cold, dark, dead world. But lucky for us, we don't have to worry about that because energy is everywhere.
Yeah, energy, you know that it is everywhere.
You need it to do anything, even comb your hair.
Kinetic energy is equal to half mv squared.
It might sound kind of funny, but please don't be scared.
You know, energy is the ability to do work.
Please use it wisely, yeah. Don't be a jerk.
There are two different types, kinetic and potential.
They're both very cool and very essential, yeah.
Yeah, there are so many types of kinetic energy.
Thermal, sound, it's kind of crazy.
You need it to run around and to warm your tea.
Now onto potential energy.
There are many different types, yeah, just like kinetic.
Gravitational, elastic, and magnetic.
Gravitational involves relativity.
Relative to the ground, the desk, or to me.
You need to measure the height, then use this equation.
That's how much energy the object has due to its location.
Now you might be wondering, what's the unit for energy?
Joules, of course, and no, not like jewelry.
See, we need energy to do everything.
You see, we needed to dance, to rap, and to sing.
I'm Aisha.
I'm Fatima, where E equals MC squared.
Now like and subscribe, come on, do it if you dare. Hey, hey.
Energy. Energy. Skirt.
Hey, energy, yeah, okay, now, energy, yeah, hey, energy, ooh, yeah, hey, okay, now, hey, okay, whoa,